So first off, the jet stream itself is a large stream of wind in the upper atmosphere. And it's typically the strongest between 300 to 200 millibars. And remember, pressure declines with height. So as you're rising, you're going into lower and lower and lower pressure levels. So the lowest elevations are in the 300 millibar level, the higher elevations are in the 200 millibar level. Now the jet stream actually forms because of a boundary between warm air down near the tropics and cold air up near the poles. And this difference in temperatures creates a difference in pressure, which creates lots of wind. Now with that said, the jet stream is typically stronger in winter, and the reason why is because the difference between warm tropical air and cold polar air is much greater in the wintertime. Whereas in the summertime, it's much smaller. And so the jet stream is typically a lot weaker in the summertime. And actually, here in California where I'm recording this, if you've ever wondered why we don't get rain in the summertime, it's because the jet stream, which actually gives us most of our rain, is a lot weaker in the summertime, so storm systems are a lot weaker. And it's usually also further north, and as a result, storm systems are not only weaker, but they also typically miss us. And that actually goes to the next point here. The jet stream is the freeway for storm systems, as I like to call it. So think of the nearest freeway from where you live. And the freeway is oftentimes like a major transportation route. It's a big thing that cars use to get very far in a relatively short time. Well, the jet stream is very much the same thing. It acts as something that storm systems travel along. So it's the freeway for storm systems. And then finally, we're going to talk a little bit about this idea of what's called zonal and meridional patterns. So if you remember from the last lab, we talked about troughs and ridges. Well, we're actually going to talk about how those relate to zonal and meridional patterns in this lab. All right, so first, let's actually talk about those troughs and ridges again. So if you remember from the last lab, I said that troughs basically look like a U shape. And then right in the center of that U, where the line stops dropping and then starts rising, that center is what's called an axis. And that divides the trough into its western half over here and its eastern half over here. And let me just tell you just a little bit about each of these halves. Areas to the east of a trough have winds that are typically coming from the south. And these southerly winds typically bring a lot of warm air with them. So you usually get a lot of warm air advection on the eastern side of a trough. Meanwhile, on the western side of a trough, the winds shift to now coming from the north, and so you get a lot of cold air advection along the western side of a trough. The other thing that's important to know is that a trough basically happens when cold air from the North Pole ends up pushing further south, creating a larger area of cold weather down here. So if you ever heard of polar vortexes, or if you've ever heard of like even cold weather that we've experienced here. I mean, just as I'm recording this, a few weeks ago we had a major snow event on many of our local mountains. And what was actually happening was there was a trough overhead in the jet stream that had pushed all of this cold air down towards us. Now, on the other hand, ridges are quite the opposite. So they look like upside down U's, almost. And ridges occur when warm air from the south is pushing northward. And just like troughs, ridges are divided into two halves. So you have this axis in the middle, and then you have the western half over here, and eastern half over here. All right, with me so far? So western half, eastern half. On the eastern half, if you notice, it looks like the winds are primarily coming from the north, maybe the northwest. There's lots of cold air advection over here. Typically on the eastern side of a ridge, so the ridge hasn't passed yet, it's not overhead yet, typically on the east side of the ridge, you're getting a lot of cold air advection. And that's also where a trough is moving away, so you're still influenced by that. So yeah, you're getting a lot of cold air advection. Then the axis passes, and then you're in the western side of the ridge, and here, winds shift to coming more out of the south, and so you're getting warm air advection. Now the next thing I wanted to talk about is the fact that these troughs and ridges aren't always very deep. And in fact, sometimes the jet stream can even have a very straight flow with very little waves. So very, very tiny troughs, very, very tiny ridges, nothing really large happening there. And this is what's called zonal flow. So zonal flow is almost directly west to east with very little waviness to it. And so that's what a zonal flow is. An image A in this figure, which this is straight from the lab, this is actually a zonal flow. So the winds, the jet stream itself is almost flowing perfectly west to east, almost perfectly straight. Whereas a meridional jet stream occurs when the jet stream is composed of very large waves. So you see a deep trough or a really broad ridge, and those patterns create a meridional jet stream. Now, it's actually very possible for you to see something like a deep trough on one side of the United States, and then on the other side, a zonal flow. So the jet stream doesn't have to commit to one or the other around the entire world. It can actually be zonal in one location and meridional in another. So wherever you see relatively straight flow, relatively straight wind flow, that represents a zonal flow. Wherever you see a very wavy flow, that represents a meridional flow. Now with that said, we actually typically look at the 300 millibar level and the 200 millibar level when we look at the jet stream. And the reason why is because this is where the jet stream is strongest. So as I said in the previous video, we don't look at different heights. Instead, we actually look at different pressure levels. And the jet stream typically hangs around 200 and 300 millibars. And so let's actually talk a little bit about the jet stream. So this is the same map that is actually on the investigation. And let's talk about what's happening here. So first off, is the flow here zonal or meridional? Well, if it was zonal, these blue iso lines, these blue contour lines, would almost be directly east to west, or directly west to east, I apologize. Whereas here, you notice what looks like a very large ridge over the western half of the United States and a very deep trough over the eastern half of the United States. This is typically very indicative of a meridional pattern. All right? So this is a meridional pattern. Now the next thing is there's certain features we look for in a jet stream. And the reason why is because low pressure systems on the surface of the Earth are triggered by what's called divergence in the upper atmosphere. And so divergence in the jet stream. And the way that we can usually identify the presence of divergence is by identifying where jet streaks are. Because along a jet streak, winds typically bunch up together. So think about if I had 50 people in a room and they all ran for the same door. They would all be converging at that door. And what happens is when winds bunch up, that creates a greater pressure gradient force and therefore a faster wind. However, as soon as you get to the other side of the door, everybody spreads out. So think of a jet streak almost like a door. And these winds typically blow from west to east. And in fact, the jet stream is actually what's called a westerly wind. It blows from west to east. So A jet stream, or sorry, a jet streak is basically like the door, where everybody's converging on the western end of the jet streak and diverging on the eastern end. And what happens is this divergence on the eastern end triggers lifting, which then can develop low pressure systems. So low pressure systems, which then end up developing into full-blown mid-latitude cyclones, actually get their beginning in the jet stream at these different jet streaks. And at the 300 and 200 millibar levels, you can actually identify jet streaks using these gold dashed lines. These are what are called isotachs. Basically what they do is they're a line of constant wind speed. So you remember isobar means same pressure, isotherm means same temperature, isotach means same wind. And these gold dashed lines represent patterns of wind. And I'm looking here, and basically a jet streak will stand out whenever you notice what looks like a bullseye. And a bullseye is an area of really strong wind. And that's what a jet streak is. So let's take a look here. Looking at this map, I noticed two jet streaks. There's one over here, over Missouri, extreme southeastern Iowa, and Illinois. Meanwhile, there is a second jet streak over here. And this jet streak is over western North and South Dakota, northwestern Wyoming, and southeastern Montana. Did I say northwestern? Sorry, northeastern Wyoming and southeastern Montana. So these are where these two jet streaks are. Now I can almost guarantee you're going to be asked some kind of question related to how many of these jet streaks are present. And typically a stronger jet stream is going to have more of these areas of faster winds, more of these jet streaks. Whereas a weaker jet stream is typically going to have slower moving winds and so fewer jet streaks. So that's what you're going to be investigating in this particular investigation. And so just real quick, the ISO lines here, these contour lines, the blue lines, work the exact same way as in the previous assignment. And what I mean by that is that they represent areas of constant height. So areas of constant height. Their interval is a little bit larger here. In the previous one, it was 60 meters. Here, it's actually 120 meters. But other than that, the same thing. And if you notice, the pattern is typically very similar as well. You have higher values further south, lower values further north, and that indicates warm air down here, cold air up here. Now, if you actually notice in this trough, these lower values travel much further south. This is why troughs bring such cold air with them, because heights are way lower here. So that's all that you need to know for this lab. Again, any questions, comments, concerns, please don't hesitate to reach out to me. We've got one more lab in this group, and that's going to deal with everybody's favorite topic, El Nino. So I'll see you for that. And then again, real quick, if you haven't done Lab 8B yet, I recommend going back and doing it before you feel comfortable doing this lab, because they both really work hand in hand. All right, so I'll see you next time.